After doing the last three examples, we should start trying to formulate what was special about the f of x that I chose that wasn't special about the g of x and the a of x. Well, with the f of x, we could find a point whose average rate of change was the same as the point's instantaneous rate of change. But for the a of x, we could not. We could not find a point where the average rate of change over the interval was equal to an instantaneous rate of change at a specific point. Now, the special part has to do with the type of function we were dealing with. And if we notice, our f of x was a really nice, smooth function. It was continuous, and there were no sharp corners. And that's really what we need with the mean value theorem. Here's the mean value theorem of differentiation. Let y equals f of x be a continuous function on the closed interval from a to b, and differentiable on the open interval from a to b. If we have this, there exists a value c such that c is between a and b, and the instantaneous rate of change at c is the average rate of change on the closed interval. In other words, there exists a c which has the property that the derivative of f at c is equal to the average rate of change over the interval. The key thing here is that the function needed to be continuous and differentiable. Differentiable, we saw earlier, means continuous and there's no sharp corners. So we need a smoothly drawn function. And if you look back at the examples we had, the a of x had a sharp corner at 0. The g of x was not continuous. But the f of x here was both continuous and differentiable over the interval from 0 to 3. So this is the mean value theorem of differentiation. Now, a corollary of the mean value theorem is what's called Rolle's theorem. Let f be a continuous function on a closed interval and differentiable on the open interval from a to b. If we have f of b equal to f of a, then there exists a value of c where the derivative of f at c is equal to 0. So if we have two function values the same, then there is a x value in between them where the derivative of that x value is 0. This is what we call a corollary, because if we understand the mean value theorem, this one is an immediate result of that. More specifically, if we let f of b equal f of a, then we can see the average rate of change is 0. So if these two are equal, then the numerator becomes 0, and so the average rate of change is 0. So the mean value theorem of differentiation allows us to know that if I have a certain average rate of change and a nice function, then the derivative of the function at a certain value in the interval will equal the average rate of change over the entire interval. Let's take a look at another function called g of x. Consider this g of x on the interval from 2 to 7. This g of x is a polynomial function. We should all know now that polynomial functions are smooth, meaning they're differentiable and continuous everywhere. In particular, they're differentiable and continuous on the interval from 2 to 7. So the mean value theorem will apply for g of x on this interval. We look at g of x and we want to find the average rate of change on the interval from 2 to 7. In the numerator, we plug in g of 7 minus g of 2. In the denominator, we plug in 7 minus 2. G of 7, plug in 7 into x squared plus 6x minus 4. That will give you an 87. If I plug in 2 into the function g of x, I end up with 12. And then the denominator, 7 minus 2, is going to become a 5. This fraction is 75 over 5, which is 15. So the average rate of change on this interval is 15. If I want to find the point at which the average rate of change is equal to the instantaneous rate of change, I simply need to take the derivative of g. Because this is differentiable, I get a nice function, 2x plus 6. I can set that equal to 15 and solve for x. Subtract 6 from both sides, then divide by 2. So the x value of 4.5 is the spot on this curve whose instantaneous rate of change is equal to the average rate of change from 2 to 7. Obviously, 4.5 is in fact in that interval. By the way, if you try to do this and graph it, it's very difficult to come up with a tangent line if you're drawing it, freehand. We know about where the tangent line is going to be, but sometimes if the x value is 4.25 versus 4.5 versus 4.3, it's kind of hard to see. So algebraically, it's much cleaner. Let's look at another example. Consider this third degree polynomial. P of x is equal to x to the third plus 12x squared minus 15x plus 8 on the interval from -2 to 6. This is a polynomial function, so we know it is going to be continuous and differentiable everywhere. In particular, it's going to be continuous and differentiable on -2 to 6. So we can find a value c in the interval from -2 to 6, which satisfies the mean value theorem. We have our function p of x. We want to find the average rate of change first. So we plug in p of 6 minus p of -2 and divide that by 6 minus -2. Plugging in 6 into the function p, 6 cubed plus 12 times 6 squared minus 15 times 6 plus 8 gives me an output value of 566. When we plug in -2 into the function, -2 cubed plus 12 times -2 squared plus 15 times -2 plus 8 gives me a 78. And then the denominator is 8. 6 minus -2 is 8. 566 minus 78 is 488. We're dividing that by 8. That's nice because that's divisible. That gives me a whole number, which is 61. By the way, we don't have to have an average rate of change that comes out to a whole number. Our average rate of change could be a decimal, or it could be 13.26. Lots of different average rates of changes out there. But ours happens to be 61. If I want to find the value of x on this interval, whose instantaneous rate of change is also 61, then I take the derivative. That's going to be 3x squared plus 24x minus 15. I want to figure out when that could be 61. And this is a quadratic equation which I can solve for x. Let's go ahead and subtract 61 from both sides. I end up with 3x squared plus 24x minus 76. There's a number of things you could do if we wanted to solve this for x, but probably the most efficient way is to do the quadratic formula. X is equal to the fraction whose numerator is -b plus or minus the square root of b squared minus 4ac, and the denominator is 2a. In our case, b is 24, a is 3, and c is -67. So x is equal to opposite of 24 plus 24 squared minus 4 times 3 times negative 76, all divided by 2 times 3. So x is equal to negative 24, either plus or minus the square root of 1488 divided by 6. If you wanted to, you can keep an exact answer, but for right now, I'm just going to get answers rounded to a couple of decimal places. So I'm going to take negative 24 and add the square root of 1488 together, and then divide by 6. One of my answers, the one when I use the add, is x is equal to 2.43 approximately. The other answer, when I use the minus, in other words, when I take negative 24 and I subtract the square root of 1488 and then divide that by 6, is negative 10.43. Again, approximately. So I got two numbers whose derivatives were equal to the average rate of change on this interval. Those two numbers are 2.43 approximately and negative 10.43. You'll notice that of those two numbers, in our case, only one of those two numbers is in this interval. So while they both have the correct instantaneous rate of change of 61, the only one that actually is in our interval that satisfies the mean value theorem is the 2.43. So we can cross out the negative 10.43 and just have one answer, which is approximately 2.43. There are examples out there in which you can find multiple x values in your interval whose instantaneous rate of change is equal to the average rate of change as well. For instance, if we had a straight line, every point on that line has the same instantaneous rate of change, and the line always has an average rate of change, and it's all equal to the slope of the line. So you could find multiple values of x in an interval which have the correct instantaneous rate of change, the correct one being the one that matches up with the average rate of change. I would like you to do the following problem. Consider k of x on the closed interval from -1 to 1. Find the value in the interval which satisfies the mean value theorem.